Entirely conceptual day.
Can you see that?
Oh, have you started it? Today is an entirely conceptual day. We're going to learn about centrifugal force. We're going to learn that there's actually no such thing as centrifugal force, that it's just a fictitious force. It doesn't really exist. Then I'm going to teach you about the principle of equivalence that relates gravitational force and acceleration. Then we're going to come back and realize that actually there is such a thing as centrifugal force, but only in certain situations that we don't deal with as high school students. So as far as you high schoolers are concerned, there's no such thing as centrifugal force, even though there actually is, but there really isn't. And then finally we're going to learn about railroads, why railroad cars stay on the tracks. And then finally, if we have time, we'll talk about banked curves, something we haven't done yet in this period. Also, I want to remind you, did I mention this already, that you'll look in your AP locker? Did I do that already?
Yeah.
Okay, great. Then here we go, centrifugal force. Centrifugal force. If centripetal force is a center-seeking force, it's a force that brings you towards the center, then what do you suppose centrifugal force does? Yeah, it brings you away from the center. A force that pulls you away from the center. A force that pulls you away from the center. Have you ever heard that statement, tempus fugit? Have you heard that saying, tempus fugit? Time flies, you know, I don't know. Well, anyway, so fugal means fleeing. So centripetal force is a center-seeking force. Centrifugal force is a center-fleeing force, a force that takes you away from the center. So let's imagine this. Imagine you have this type of, let me draw a better drawing of that. Okay. Imagine you've got one of those merry-go-rounds that used to be on playgrounds, but a lot of playgrounds have gotten rid of them because they're unsafe, they're dangerous for children. How many people have ever been on one of those types of merry-go-rounds? Yeah, they're incredibly fun, right?
Yeah.
Sure. You just go faster and faster and faster until you fly off. What could be more fun than that? So when I was about 9 years old, I went to a park and I got on this merry-go-round thing, and then all of the big kids got around it and then made it go really, really, really super duper fast. Until pretty soon, centrifugal force pulled me off and flung me off into the gravel, where I went rolly, 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 and then I cried. I cried bitter tears. But was it really centrifugal force that pulled me off of that thing? Let's take a look. Let's look straight down on this merry-go-round. Let's look here. Here's me, correct? I'm moving around in a circle that's going faster and faster and faster, by the way, but I'm moving around in a circle. Tell me, what force is making me move around in a circle? Assuming I'm not like hanging on to anything, what force is keeping me moving in a circle? Say again, Justin?
Friction.
Yeah, friction. Friction between my feet and the merry-go-round, correct? Friction is making me go round and round. But what if I go so fast that the friction force isn't enough to keep me going round and round? Tell me, which direction am I going to fly? How many people say I'm going to fly that way? How many people say I'm going to fly that way? Hey, good for you guys. Yeah, I'm going to fly tangent to the circle, correct? When you stop having your centripetal force, you fly off tangent to the circle. In the same way that I demonstrated for you guys, earlier, when I have this thing, if I let go of the yo-yo right there, which way is the yo-yo gonna fly? Yeah, straight up, right? Because when you let go, it flies tangent to the circle it's traveling in. So is there centrifugal force forcing me off? No, it's just me, it's my inertia, my desire my propensity to travel in a straight line, right? That's all it is. No one has tied a rope around my waist and is pulling me off. There's not a big spring attached to me pulling me off. I mean, all it is my desire to go in a straight line. Now, here's the thing though. While I'm flying off tangent, the merry-go-round is still rotating, isn't it? So while I'm flying off tangent, the merry-go-round is rotating. So from my point of view, I'm not flying off tangent. From my point of view, I'm seeing this guy. Imagine my eyes are right there. Okay, I see that guy, and then as I fly off tangent, I just look like I'm going towards that guy until finally, boop, I hit that guy. So doesn't it seem like I'm being pulled off radially? I'm being pulled off by centrifugal force? But no, it's just me going tangent to the circle and the merry-go-round continuing to spin. Let me go even further than that. Suppose I slide all the way off until finally I'm right here, okay, hanging on for dear life. Okay, so I'm whipping around, hanging on for dear life. If I let go, what direction do I go? Do I fly out this way? Which direction do I go? Tangent. I'm going to go off in that direction, correct? Now, it may feel like there's centrifugal force. That is, look at my hands. My hands are holding on to something, and I'm holding on as hard as I can, okay? Doesn't that mean that there's this big monster, the centrifugal force monster? Centrifugal force. Okay, here, he's got me by one ankle, and he's got me by the other ankle. Okay. Isn't the centrifugal force monster pulling me by the ankles so that I'm barely holding on? No. Someone tell me, why do I have this feeling of force on my hands? Why does it feel like, oh, I'm holding on, there's someone who's got me by the ankles and pulling me? Actually, what's responsible for the force that I'm feeling on my hands?
Tension.
What's that?
Is it tension?
Well, not tension per se. I mean, maybe, but there's no rope or wire here. There is a force, though.
Inertia.
Well, inertia makes me want to go in a straight line. So in order for me to keep going in a circle, I need a force. So the force is, I guess, overcoming inertia or having to battle against my inertia to keep going in a straight line. But let me ask again. My hand feels like it's pulling away on the bar. Why is that? Yes? Well, tell me, what's making me go around in the first place? Why am I going around in a circle? Before I let go, why am I going around in a circle? What's giving me the centripetal force for me to go around in a circle?
Friction.
Not friction. I mean, I wouldn't call that friction. What kind of force would you call this? When this thing is, when I'm, pressed here. Yeah, normal force. You guys okay with that? This is normal force. Do you see the bar is exerting a normal force on me towards the center of the circle? The bar is exerting a normal force on my hand towards the center of the circle. Okay? And because the bar is exerting a force this way on my hand, what's my hand going to do to the bar? Exert a force in the opposite direction as well. Exactly. You see? So I want to summarize this by saying there's no such thing as centrifugal force. I'm not being pulled off radially. I'm actually just falling off in a tangent direction, which means there's no force on me. An object in straight line motion remains on that motion unless a force acts on it. There's no centrifugal force acting on me. It's just me going in a straight line, like Newton's first law says. And it may feel like centrifugal force is pulling me out, but it really isn't. The feel I have of force on my hands is just a Newton's third law reactive force to the fact that the bars are having to exert a force inward to keep me moving in a circle. So there's no such thing. Any questions or issues on this? Okay, then let me talk a little about the principle of equivalence. Principle of equivalence. Now, the principle of equivalence is actually a kind of a complicated thing that I'm not going to teach you all about. I'm just going to teach you one little aspect of the principle of equivalence. But Albert Einstein used the principle of equivalence in his development of the special theory of relativity. So that's where I encountered it for the first time, really. And so I'm going to teach you one little part of it. Principle of equivalence. Here we go. Okay, so here's a high bar, and here's a guy hanging off the high bar. Tell me, let's say this guy is hanging, his acceleration is 0. Let's say this guy is spinning around, and his acceleration is 9.8 meters per second squared. Is this guy going to feel any different as far as his arms and his hands go? Is that guy going to feel any different than this guy? Logan, you shake your head. Why?
Because the acceleration of gravity is down at 9.8, and he's not really experiencing gravity. He's experiencing the normal force at 9.8.
Good. Beautiful. You guys okay with that? I mean, this guy has two forces acting on him. Gravity, and we'll call it, just like Logan said, the normal force of the bar on his hands upward. And so he's at rest. This guy, he's not experiencing any gravity, but he's experiencing acceleration, right? Oops. He's experiencing acceleration. This force here, the force on his hands, is the normal force that the bar exerts, no different than that. And that normal force ends up being m times g, because I just told you that the v squared over r is 9.8. Do you see that this guy's not going to feel any different than that guy? Even though he's accelerating and he's not. He's just in gravity. He's just in the presence of gravity. Here, let me give you another scenario. I've got this guy just standing there on the ground. And then I've got this guy in outer space in a rocket ship. And the rocket ship is accelerating upward at 9.8 meters per second squared. Does this guy feel any different than that guy? Consider their apparent weight. This guy's just on Earth. What's his apparent weight going to be? His normal force? mg. What about this guy's normal force? There's no weight on him. He's in outer space. He's not near any planets or stars. But what's his normal force going to be? Someone say it. What's his normal force? Here, some of the forces equals ma. The only force acting on him is normal force. That's all he's got. What's his acceleration? 9.8. So does this guy feel the same as this guy? Sure. Why not? They both feel the same apparent weight. His apparent weight is mg. His apparent weight is mg. And that gets me to the principle of equivalence. The principle of equivalence says you can't tell. There's no difference between being in a gravitational field or accelerating. They both feel the same. They're equivalent to each other. Being in gravity or accelerating feel the same. In fact, under the right circumstances, you couldn't even tell the difference. You couldn't tell the difference between this and this if your eyes were closed and you didn't have the feeling of the air whipping around you as you went round and round. How could you tell the difference? You feel a force, that's it. There's something else I've got to tell you, something that no one has shared with you before now, because they thought it might make you kids concerned. We don't live on a planet. The sky, the media telling us we live on a planet, that's just all a ruse. We actually live on a rocket ship. All of us are on a rocket ship that's accelerating 9.8 meters per second squared. Did you know that? Good. I'm glad you nodded. Yeah. So if you think, I mean, I hate to disabuse you of this notion that we live on a planet, but we don't. We live on a rocket ship. Everything else is illusion. Are you guys okay with that? Yeah. So now I don't know where we're headed. Someone's in charge, I'm sure, steering this rocket ship that we call Earth, but that's where we are. We're on a rocket ship. And could we tell the difference? Nope. So that's where we are. Sorry. On a rocket ship. Now, I want to talk a little about centrifugal force. Remember how I said it's fictitious, it doesn't really exist? Well, it does kind of exist. And let me tell you under what circumstances, okay? I got to define something called an inertial reference frame, okay? Inertial reference frame. You know, inertial reference frame. All the measurements we make are relative to us, right? When I measure the velocity of a car, I'm measuring it relative to me. I'm at rest, and so I can detect the motion of the car and measure its velocity. But it's always relative to me, right? Any measurement you make is relative to something, and so what your measurements are relative to, that's called your reference frame. All the measurements we make in this room are relative to the reference frame of the room itself. You see? Well, an inertial reference frame is a reference frame that's not accelerating. A reference frame that is not accelerating. When you're in a reference frame that's not accelerating, then all of these rules we learn work just perfect. And in fact, all of these rules are what we learn in high school. So high school physics, we're going by the presumption that every measurement we make is with an inertial reference frame, a reference frame that's not accelerating. Let me show you the problems that occur when you have a non-inertial reference frame. Here. I've got myself a frictionless turntable. Let's pretend it's frictionless, okay? And I've got a spring attached to the center of the turntable, and I've got a mass at the end of that spring. And the turntable is rotating, and I'm sitting on that mass, okay? Suppose I looked at the mass relative to me. Suppose I proclaimed myself the reference frame. Now, I'm on a rotating reference frame, so I'm rotating. I'm not an inertial reference frame. But suppose I said, hey, I'm going to make all the measurements relative to me. As far as I'm concerned, I'm at rest, okay? And I'm going to make my measurements relative to everything else, given that I'm at rest. Well, let's look at this mass. And let's look at the spring. I detect that the spring is elongated, the spring is stretched, which means the spring is exerting a force to the left on this mass, correct? Spring force. This mass is not moving relative to me. Relative to me, the mass is at rest. But all I've got is a single unbalanced force on that mass. All I've got is spring force. I know there's spring force because it's an elongated spring, so I know it's exerting a force to the left. But this mass isn't moving. It's at rest relative to me, so I can't have an unbalanced force. Tell me, what is the force balancing the spring force? I'll tell you, centrifugal force. Centrifugal force. Now the problem is, there's no agent responsible for that centrifugal force, right? I don't have a rope tied around the mass. There's not a big magnet on the mass and a magnet over here. I mean, there's nothing causing the centrifugal force, but I know it must be there because I can't be at rest and have an unbalanced force. So there is indeed centrifugal force. But because nothing's actually causing it, even though I know it must be there, because look, that's why we call it a fictitious force. Because it doesn't actually exist, but in order for my physics to work out okay, it has to be there. It's the force causing that mass to move, to be stretching the spring, essentially. It's the force that's pulling that mass to the right so that the spring has to stretch to balance that force, even though that force doesn't actually exist because there's no agent responsible for the force. But it's still there. Relative to me and the mass, it's there. You guys okay with that? So you can have centrifugal force. In fact, can I just ask you this question? Are we really in an inertial reference frame right now? Why not? Yes, let's go ahead and say it. Or tell me, Noel. Why not? Why are we not in an inertial reference frame?
Because the Earth is accelerating.
Because the Earth is rotating, right? The Earth is rotating. So all the measurements we make are like this dude on the mass. And so we have to take into account the fictitious forces. And so yeah, when you do any real serious physics, making measurements on this rotating Earth, you have to take into account centrifugal force. There's another force. I mean, for example, when you're on Earth, okay, you're on the equator of Earth, okay. Gravity is pulling you down. Normal force is pushing you up, but relative to you, there's no other forces acting on you, yet your normal force is less than your weight, right? Your weight is this, your normal force is just this. Relative to you, you're at rest, so you're going, wait, there must be another force acting on you. And the answer is, yeah, centrifugal force. That's what's pulling you away from the center of the Earth. Now, relative to a guy standing here, right? This guy isn't going to see centrifugal force. This guy's just going to see spring force. And what else is this guy going to see? My blue man, what's he going to see? I wonder if it's making sense to you guys. He sees spring force, and what else does he see this guy doing? Go ahead, Noel.
He sees the guy spinning around on the turntable.
Yeah, he's spinning around on the turntable, which means, well, what is he doing? What? Yeah, thank you. He's accelerating. So this guy's going to go, hey, dude, you're crazy. You only have one force on you, and it's responsible for you accelerating. And this guy's going to say, I don't know what you're talking about. I'm not accelerating. I'm at rest. You see what I mean? And that's the problem between being in an inertial reference frame and being in a non-inertial reference frame. As far as he's concerned, he's at rest. This whole idea of the one single force causing mv squared over r makes no sense to this guy. And it's the same thing as being on planet Earth. So the measurements we make, we have to consider, actually there's 3 fictitious forces we have to consider. One of them is centrifugal force. The second one, has anyone ever heard of something called the Coriolis forces? Or Coriolis effect? Anyone ever hear of that?
Is that the thing that causes something, it has to do with the oceans, I think.
Yeah, or the atmosphere.
Yeah.
Yeah, absolutely. And this is an artifact of us being on a rotating reference frame. So we have to. This is a fictitious force. There's no actual agent causing Coriolis force, you know. But we have to consider it because we're on a rotating reference frame. And the third one, if I'm not mistaken, is called Euler's force. And I don't know anything about that, unfortunately. I'm ignorant about that. But anyway, so I just wanted to let you know. But as far as high schoolers go, you little cute little high school students, there's no such thing as centrifugal force. You guys okay with that? It's just your desire to move in a straight line, tangent to the circle, and any force you feel is because of Newton's third law effect of the force that's giving you the centripetal force. Alrighty. Well, hey, that's that. Here, let's learn about railroads. Alright. Tell me, what keeps railroad wheels on the tracks? Why do railroad wheels stay on the tracks? What's that? Friction? Okay. Here, let me even make you a drawing. Here's a track. Here's a track. Here's my wheel. Have you ever seen railroad wheels up close that they have flanges on them that surround the track? They keep you on the track, the flanges. In the same way, how many people have here gone on Autopia in Disneyland? Okay, yay. I love it. Autopia. What you've got is this cement island, and then you've got the wheels of the car. Okay, and then you let your 6-year-old drive, confident that he's not going to get in a crash or something because he can't depart from that island. But you know what happens when you're driving? What happens with the car relative to the island? Yeah, you just go bang, 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 bang. It's not a very pleasant ride. You're trying to tell your 6-year-old, honey, try not to hit the island because it'll be a more pleasant ride. But you just go bam, bam, bam. Okay? Well, do you see that that's what would happen if those flanges were actually keeping the wheels on the track? Tell me, first of all, what are you going to get with these metal flanges constantly rubbing against these rails at 60 miles an hour? What's it going to look like? Yeah, you're going to get sparks. You're going to get a shower of sparks. And you know that doesn't happen. Don't get a shower of sparks when you see a train going by. So these flanges aren't actually what keeps the train on the tracks. And I'm going to teach you now what keeps the train on tracks. That's what we're going to do now. Cup. Red cup. Tell me, if I take this cup and roll it that way, which direction is the cup going to curve? Is the cup going to curve to the right or to the left? Let's see. If you chose right, you're correct. Here it comes. You guys okay? It curves to the right. Okay. Let's go ahead and ask why. Look at these 2 black X's. You see the 2 black X's? Great. Tell me, as the cup is rolling, which black X has the higher revolutions per minute? Which black X has the higher rotational speed? How many people say this guy's going more revolutions per second? Okay, good for you guys. How many people say this guy is? Okay, is there a third choice? The same RPM? Does anyone think these 2 X's are going at the same RPM? Here, well, let's go ahead and do it. I'm going to rotate the cup 1 revolution. I'm gonna rotate another revolution. So what can you tell me about the RPM of those two x's? They're the same, right? Right, they're connected to each other. One guy's not gonna do more revolutions than the other guy because they're connected. You guys okay with that? Okay, great. So they're gonna do the same revolutions. So tell me, in one revolution, who goes farther? This guy does, because he's got the bigger circumference, right? So in one revolution, this x has to travel a farther distance than that x. And that's why the cup has to curve, right? The only way you can roll the cup but have this x go a farther distance than that x is for the cup to move in a circle. You see? For the cup to curve. You guys okay with that? Okay, so let's go ahead and talk about railroad tires. Your railroad wheels don't look like this. They actually look like this. They look like two cups connected with a solid axle, an immobile axle. That's what your railroad tires or railroad wheels actually look like. So here's one rail, here's the other rail. If the same part of the two cups, the same part of the two wheels are at the rail, then the train rides straight, the train rolls straight. But what if my train drifts to the right? What if it drifts to the right? So I get this phenomenon where this wheel now is looking like this. Okay? And this wheel is looking like this. Whoops. I went too far down. Okay. Do you see now that this rail is in contact with the small circumference part of the cup, and this rail is in contact with the big circumference part of the cup? Tell me, which direction is this railroad train going to want to turn? Small part of the cup, big part of the cup. Which way is it going to want to turn? Hopefully you're thinking to the left, correct? So my train that drifted to the right will naturally want to adjust itself and go to the left, because that's the way this cup would curve. Big circumference, small circumference. You see? Let me actually demonstrate this for you. Here's my railroad train tires, but rather than having this immobile axle in between them, I just actually put the two wheels together. Let me set up my railroad tracks. Whoops. Alrighty. And so now I want you to see that as it rolls, it naturally rolls straight, though my railroad tracks aren't really cooperating that well. But even if I roll it to the right, if I roll it to the, oops, science is a lie. If I roll it to the right, it naturally comes back. You see? It's always adjusting itself. It never leaves the track. Here, let me actually have this guy curve. Just a second. Here, I don't have to have a driver with a steering wheel. The railroad train just automatically makes the curve. See what I mean? It just, it hit here and it was displaced too far to the left for that track. And so it just automatically adjusted. I don't know, do you believe in railroad tracks and a railroad train? So that's why they do it. You're not depending on the flange. Now, the problem is, of course, the steering only can happen while it's in motion. right? So what do you do to make sure it doesn't leave the track while it's not in motion or at very low speeds? Well, that's where these little flanges, I guess, come in. That's all I can figure. But this is why, because we're depending on this to keep a railroad train on the tracks, this is why it's so easy to knock a train off the tracks. You know what I mean? All I got to do is park a pickup truck on the railroad tracks, and this train slams into it at 60 miles an hour, and now you're not going to get this nice little gradual adjustment. You're just going to get a train that leaves the tracks, and then a bunch of people get hurt or die, you know, which is a bummer. All right, so hey, that's it for railroad trains. Any questions or problems on that? Okay. Let me see. We've got time to talk about finally the banked curves. So I'm gonna say 1 minute on bank curves. You didn't turn that off yet, have you? Okay, thanks, Leilani. You should like every time you should put your face in front of the camera so that everyone will know. So in 20 years when I'm looking at these videos, looking back on my life, on my wasted life, I can see you. Hey, banked curves. This is our third or fourth conceptual thing. It's only going to take a minute. I just need you to see why banked curves help. Why do banked curves help? Why do we bank curves? Okay? Like, let's say I want to move in a circle. I've got a car moving in a circle. Alrighty. And I think, well, shoot, I've got gravity down. I got normal force up. And I got static friction force between the wheels and the road. And that'll help me make this curve. Why do I need to bank a curve? Well, let's see what banking a curve does for you. Now, instead of you running on a flat surface, you're running on a slightly banked curve. That's a pretty severely banked curve. Let's go on a slightly banked curve. So here's my banked curve. And now here's my car. Alrighty. Here's the center of the circle that the car is driving in. But the curve is banked. Now, gravity is still going down. Friction force is now going along the ramp. And normal force is perpendicular to the ramp. So you look at the friction force, and it used to be all the friction force was horizontal, so all the friction force was allowing me to make my curve, giving me the centripetal force to make my curve. Now it's just the horizontal component of friction force. But you know, it's pretty close. I mean, the horizontal, it's a pretty small angle. The horizontal friction force is pretty close to the entire friction force. It's still doing the job for me. Tell me, what do I gain by banking my curve? Why would I bank it? Am I gaining any additional centripetal force to make it easier for me to make this curve? Where's that additional centripetal force coming from? Yes, Logan.
The x component of the normal force.
Thank you so much, Logan. Thank you. We would have been here all day waiting for someone to come up with that answer. Thank you so much, Logan. And it's on video for posterity. Yeah, look at this normal force. You're getting this humongous x component of normal force, right? Way more than what little teeny bit of friction force you lost. You gain a stupendous amount of normal force. And so yeah, by banking the curve, you gain a bunch of normal force. You get more centripetal force, so you make less demands on friction to help you complete the curve, and you got your normal force. And in fact, the more you bank the curve, the greater the normal force is, and then the less requirement you make on the friction force to allow you to complete the circle. They tried to do this sort of thing at the Indianapolis 500. They banked the curves more than they ever had before. And so the drivers were able to go around the curves faster than they ever had before. And you know what the driver started doing? They started blacking out. They would black out in the curve, just like an airplane guy who does too deep of a dive. Yeah, they black out for a moment. And so then like they go, oh my God, I blacked out, and then I woke up just in time to not die. And at that point they realize, well, we better not bank those curves. So they have to bank the most. Now there's rules governing how much you bank the curves because they don't want the drivers blacking out, all the blood rushing away from their brain and blacking out, then they crash and die. So anyway, thank you. Thanks for coming. Bye-bye, video.